Hello everyone. In this video, we'll explore the Kullback-Leibler divergence or KL divergence for short and see how it helps us approximate one probability distribution with another. Here, we have two distributions P, the truth, and Q, our model. So what does KL divergence actually measure? Imagine you encode data that really comes from P, but you use a code built for the wrong model Q. You waste bits. KL divergence is the average number of those extra bits. For each outcome, we weight by how often it truly occurs. P of x times the log of ratio P over Q, the surprise gap. Equivalently, it's the cross entropy minus the entropy. KL divergence has three properties. First, it's always non-negative and exactly zero when Q perfectly matches P. Second, it's asymmetric. Swap P and Q and you generally get a different answer. And third, it breaks the metric axioms, so we call it a divergence, not a distance. This idea shows up everywhere in statistics. Maximizing likelihood is essentially minimizing KL. In machine learning, it's the cross entropy loss, t-SNE, and information gain. And in deep learning, it powers variational autoencoders, diffusion models, and RLHF. One idea everywhere, make a model Q close to reality P. Finally, let's put it to work. We want the best Q, the one that minimizes the KL divergence to our target P. Watch as we adjust Q's mean and spread step by step, the divergence fall until Q settles right onto P. The same idea works for any distribution. In the next section, we'll do exactly this in Python. Coming to the practical side of the things, what we are going to do here is we are going to approximate a binomial probability distribution with another distribution using the KL divergence statistic. So to establish the binomial distribution first, what we are going to do is we are going to run this part of the code. Now to visualize this binomial distribution, think about a situation where you are doing a repeated coin toss. So we are doing this coin toss a total of 100 times, and the random variable or the outcome that we want from this experiment is how many times out of this 100 tosses do we see a head turning up. So that would be the random variable here, and the probability that I am defining for the heads to come would be like 5%. So naturally, this would mean that the total number of heads that will come across those 100 coin tosses should be on the lower side. This activity will be repeated 1,000 times again for this to become like a distribution. And what I will do now is I'll run this part of the code to showcase how the random variable looks like. So over here for the top 50 or the first 50 observations across these 1,000 trials, you see small numbers, generally less than 15 over here, which says in the first trial, 4 number of heads came, followed by 5 heads, 3 heads, 7, 11. So you see that the number of heads is pretty low. That is because of the fact that the probability here is defined to be pretty low. Now, if I flip this to, let's say, 0.95 and I rerun this, what you end up seeing is a very, very high number of heads coming across in each trial of 100 tosses. So first one has 90 heads coming up, followed by 93, 93, 93, 94. So if we keep switching this probability, it determines what kind of numbers we'll see. Now, in a practical approximation exercise, we will not have access to these parameters. So what we will instead have is this. So this array, which will be provided to us, and then we will have to create the probability distribution from this. And then once the probability distribution is created, we'll have to approximate it. So going to the second step, which is creating the probability distribution, if I run this, what we see over here is a graph which has a long tail on the left side, so it's a left skewed. and majority of the observations are on the right side. And if you see, whenever in a typical binomial distribution, if you have worked with it, whenever you see on the, if it is coming like this, where the probability is on the higher side, you can estimate what would be the n, because there will be a lot of cases where you will have 100 out of 100 coin tosses coming to be as 100 heads appearing. So one parameter out of the two, which is the n and the p, we can determine that, yeah, n has to be 100. So one of the parameters has been estimated here. Now what we have to do is estimate the probability parameter, which I have currently set as 0.95, but we don't know just basis this array. So the next step would be to run this, and here is where we do the approximation. Over here, what we are doing is we are creating the probability list. So we are starting with the smaller probabilities and then incrementing it in each step, making it closer to 1. And then what we are doing is we are creating a couple of approximation binomial distributions where n is 100, as I discussed, and the probability list is starting from a value close to 1 and coming to a value close to 1. We will be creating these distributions one by one, and what we will do is we will compare each of these approximated probability distributions with the original probability distribution using the KL divergence and create an array of the KL divergence itself. So we can determine at what value of the probability P does the KL divergence become the least. So that specific part of the construct will be tested by this part over here. So if I run this, what we do see is this KL divergence curve, which is coming down. It continues to come down with incremental values of the probabilities of success, which is the probability of heads here. And it flatlines around 0.8 to 1. So the real answer has to be somewhere in between. And if we see, the code has estimated that the probability parameter has to be 0.95, which is exactly the same which we had provided over here. So using this code, I am able to also approximate what would be my probability parameter, which is 0.95. Now let's check this with different situations. So now let us create a coin which is fair. So the odds of coming a head and a tail are equal. And you see like evenly distributed values coming up. And if I replot this, so it's more looking like a normal distribution now centered around 50. And if I again run this code, now you see that it's not just flatlining near 0.8 and 1, but it is showing a dip in the middle part. And again, the estimated best value for the parameter, it is showing as 0.5. Now, in the third scenario, let's make it 0.05, where the chances of heads appearing is very, very low. If I rerun this and I run this, then we see that the tail on the right side starts to increase, making it right skewed, and majority of the values starting to come towards the lower side. And if I rerun this, so it creates like a different kind of KL divergence curve, but what it has estimated this time, again very close, is 0.06, and what we are using is 0.05 over here. So yeah, I mean, we have the total number of coin tosses, which is 100 estimated along with P every time. And if we have these two values available with us, then you can easily define the binomial distribution, which would be very, very close to the one which is provided here. So basically, this is something which can be used to do the approximation of any sort of distribution using the KL divergence method. Here I have used the example of binomial distribution, but yeah, you can use the same code construct to do this approximation for any different kind of probability distribution. Thanks for watching this video. I hope you enjoyed watching it. If you found this video helpful and learned something new, then please like and share this video and subscribe to my channel. See you in the next video.